Now that we've introduced the basic idea of magnetic fields exerting forces on charges, I want to discuss a little bit what happens when you have both electric and magnetic fields. Now, this isn't something that the book actually introduces in detail in the chapter, but it comes up in many calculation problems. This is something you're going to see frequently on assignments, and so I want to take some time to really present it. So the first thing is that you need to remember back to the beginning when we learned about forces half a year ago. We know that particles are going to travel in a straight line at a constant speed if the net force is zero. There might be more than one force acting on the particle, but if the total force, net force, is zero, then it doesn't accelerate. It travels in a straight line at a constant speed. So you're going to have situations like this, where your charged particle is traveling in a straight line at a constant speed, but it is in two fields. Now, usually, for the sake of simplicity, we're going to say that those are uniform fields. So as you can kind of see here, we have a uniform electric field pointing up. We have a uniform magnetic field pointing into the page. What creates a uniform electric field is a parallel plate capacitor. What creates a uniform magnetic field is a solenoid. So if we say that this is happening, then what's happening is that the straight line, zero acceleration, our net force must be zero. Now it's a charge in an electric field, so that means there's an electric force. It's a moving charge in a magnetic field, so that means there's a magnetic force, but they can cancel. They can be opposite in direction, equal in sign. So the only time that that is going to happen, the only time that that can happen, assuming that it's a moving charge particle, is that the fields are perpendicular to each other and they're perpendicular to the velocity vector. And this is going to depend on both the velocity and the field strengths. We can have two fields here that are oriented in these directions that don't actually cancel. So the canceling depends on the velocity itself and the field strengths. So let's think really quickly about the direction here. So to get the magnetic field direction, we do V cross B. And so if we do V cross B, that would actually be down. So V cross B would give us the down direction, but note that this is a negative charge. So our magnetic force is actually in the up direction. Well, now let's think about the electric field. So the electric force is just going to be given by Q times E. And we see that our electric field is up. But since Q is negative, we actually are going to have that our electric force, you could call this sub E or sub Q, is going to be down. It goes away from the field direction. So you can see that the two directions are opposite. So as long as everything else works out, you're going to actually have the same magnitude. So that's something to note. Do be ready to see those types of calculations, and the first step is always making sure you understand the direction. Anytime you see a problem like that, make sure that you draw the free body diagram, you actually think through the forces carefully. Now, something I want to quickly warn you about is that there are actually two separate types of problems that will involve both electric and magnetic fields. One is when the fields are simultaneous, like the one I just did. A particle is traveling through a section of space where there is both an electric and a magnetic field. These are usually going to be uniform fields. And in that case, the forces can cancel, the particle can travel in a straight line. However, there is a different type of problem where you have an electric field in one portion of space and a magnetic field in the other. So note that this portion of space here has the magnetic field. But in this portion of space, we actually have an electric field. How do I know that? Well, it's a parallel plate capacitor with a potential difference across of it. So if we have this potential difference, we know that it's going from positive to negative, and we have this electric field going up in here. So please make sure that you recognize that in this situation, we first are accelerating our particle. It first has a force due to the electric field, and then it has a force due to the magnetic field. And in the next video, we'll actually talk about the circular motion that it experiences, but this has two portions of motion. You need to calculate them separately, you need to model them separately. And in this case, it actually, in the end, spits the particle back into this region of space, though that's a little bit unusual. So in this case, it's sequential. You have one region of space with uniform electric field, a different region of space with uniform magnetic field. The last thing that I want to warn you about is that your magnetic field might not be uniform. Remember, the only thing that creates a uniform magnetic field is a solenoid, the inside of a solenoid, and technically a toroid, which is just a slightly different version of a solenoid. So now note that if we have a charged particle moving near a wire, that magnetic field varies in strength depending on the distance you are from the wire. So in this one spot in space, we can calculate what the force is on the particle. And the particle is going to experience an acceleration upwards, right? It has a force upwards, and it's also traveling to the right. But that means that the velocity direction is going to be changing. Again, we'll talk about what that usually means in the next section. But the other thing to notice is once the particle starts moving further away from the wire, no longer is it in the same magnetic field. So part of the reason that we actually work with uniform magnetic fields is that otherwise we actually have a changing force and a changing acceleration. And remember that those simple calculations we did in mechanics all were for constant acceleration. So be careful. Remember that many situations would give us non-uniform fields, and in general we're not going to do those calculations the same way. You might have to think about this problem in a different manner, but do just be careful about that.